Hey guys, Mr. Backerberg here. In this video, we're going to look at motion along a line. So if we've got an object that's moving along a coordinate line such that we can measure its position, which we're going to call S, at any given time t, then the displacement of that object over the time interval from t to t plus delta t is this delta S. So it's the change in its position. So what we do is take f of t plus delta t and subtract off f of t. So f of t plus delta t is like your ending position minus f of t, that's where you started measuring where you were at. Now if we want to find the average velocity of that object over that time interval, then this v sub av, that's the average velocity. So what we do is take the total displacement over the travel time. So we would say that's delta s over delta t, or if we're looking at that delta s like we just did on the previous slide, that's f of t plus delta t minus f of t, and then we're dividing all of that by delta t, so the change in our time. So the average velocity is measured over a time interval, but if we want to talk about the instantaneous velocity of an object, then that's the velocity at a specific time. So the instantaneous velocity of our object is the derivative of that position function s, which we're going to let equal f of t with respect to time. So at a time t, we can say that the velocity, or this v of t function, is the derivative of that s position function with respect to t. So that's going to be the limit of f of t plus delta t minus f of t all over delta t as delta t is approaching 0. So as the change in your time interval is approaching 0. So in this example, we're looking at finding the velocity of a race car. So this graph down in the corner shows the time to distance graph of a specific race car. The slope of the secant line from P to Q represents the average velocity over the 3-second interval from 2 seconds over to 5 seconds. So if we wanted to compute the average velocity, we'd have to approximate some data points in here. So at a time of 2 seconds, if we look, this is maybe a little bit above halfway, so maybe that's 60 feet that we've covered. And then at 5 seconds, if we look, that's about halfway between 300 and 400, so we could call that 350. So if we want to find the average velocity, we would look at the change in position. So if we subtract those two values, 350 minus 60 is a change of about 290 feet over that 3-second time interval. So this is going to be about 96.67. So over that 3-second interval, we could say that our average velocity was about 97 feet per second. Now, if we wanted to find the instantaneous velocity, so maybe here at point P, then that tangent line would be the velocity at that specific 2-second time value. Now, before we go too far, just a little bit more about velocity. Besides telling how fast an object is going, velocity is also going to tell you the direction of that motion. So if your velocity is positive, then your object is moving forward, or if you're tracking something moving up or down, then a positive velocity would mean that the object is moving upward. If your velocity is negative, then you can say that your object is moving backwards or down. And if your velocity is 0, then whatever your object is, isn't moving at all. Now, when we talk about speed, speed doesn't really care about the direction of travel. Speed is just how fast something is going. So speed is the absolute value of velocity. So we can say speed is the absolute value of that v of t, or we could say that speed is the absolute value of ds dt, so the derivative of that position function with respect to time. So what we're going to look at doing next is reading a velocity graph. So we've got a student walking around in front of a motion detector that records her velocity at 1-second intervals for 36 seconds. She stores that data in her calculator and then uses it to generate a time velocity graph, which is shown below here. And I'll scroll down in just a second. We're going to work on describing her motion as a function of time by reading that velocity graph. And what we eventually want to figure out is where her speed was the highest, or where her speed was a maximum value. So this graph represents the velocity that our student was walking. And like I said, we're going to describe her motion. So this graph not only tells us how fast the student was walking, but it also tells us what direction she was walking in. So right here in the beginning, where this velocity is positive and going up, that's where she was starting to walk, and she's walking forward at an increasing speed. And then where this flattens out, she's still walking forward, but now it's at more of a constant speed. Then we've got this dip in the graph. So the velocity is still positive, so she's still moving forward. It's just that the quickness, the pace, is decreasing until we get to this 0. So for a very brief second, she actually stops walking. Now down here, we've got a negative velocity. So negative velocity means she's walking backwards, and because we're getting further away from 0, she's walking backwards at an increased rate until a specific time when she's still walking backwards because the velocity is still negative, but now that rate is decreasing again until we get to this point right here on our graph. And then we're at 0 for quite a while. So she stands still for a while before she starts walking forward again at an increasing rate. So the velocity is positive, but the velocity is also getting higher. So she's walking forward at an increasing rate. So that describes her motion, but we said we also wanted to figure out when her speed was a maximum. So speed is the absolute value of velocity. So as we're looking at this velocity graph, we're really looking for the place where it's furthest away from 0. Positive velocities just mean you're moving forward. Negative velocities mean you're moving backwards. But the further you are away from 0, the higher your rate of speed is. So I'm looking down here at the bottom of this negative curve. That point is the furthest away from the x-axis, so that's got the highest rate, which would have the maximum speed. So when she was walking backwards, she achieved her highest speed. Now, acceleration is the derivative of the velocity with respect to time. So if we know that an object's velocity at a time t is v of t, or ds dt, then the object's acceleration at a time t is a of t, which would be dv dt, or we could say that's the second derivative of s with respect to time. So we could say that's s double prime. Now, some of the earliest questions that motivated the discovery of calculus dealt with velocity and acceleration, particularly the motion of a free-falling object. People like Aristotle and Galileo and Isaac Newton all studied falling objects and tried to come up with a way to represent the distance that they had fallen based on a time. And what they discovered was that the distance an object that's released from rest falls freely is proportional to the square of the amount of time it has fallen. So we've got this equation s equals 1/2 gt squared, where s stands for the distance that our object has fallen, g stands for the acceleration due to gravity, and t stands for our time. Now, depending on how we're measuring things, our equations might look a little bit different. If we're using standard English units where we're measuring things in feet, then the acceleration due to gravity is 32 feet per second squared. So in our equation that we just looked at, the g value would be 32, so it'd be 1/2 times 32 times t squared, which we can then simplify down to 16t squared, and we're measuring s in feet. But if we're using metric units, then the acceleration due to gravity is 9.8 meters per second squared. So then our equation would say 1/2 times 9.8 times t squared, or we could write that as 4.9 t squared, and this time our distance is being measured in meters. So in this example, we're going to be modeling some vertical motion. So we've got a dynamite blast that propels a heavy rock straight up with a launch velocity of 160 feet per second, which equates to about 109 miles per hour. It reaches a height of s equals 160t minus 16t squared after t seconds. So this function models the height of this rock at any given time t. And the first thing we want to figure out is how high does this rock go? So we're trying to find the maximum height of this rock. So if we think visually about what's happening here, this rock got blasted up, and then eventually gravity takes over, and then it has to come back down. We're trying to find the highest point on here. Now, at that point, the tangent line, or the velocity of the rock, would have a slope of 0. And when we're looking at our position function, if we do the derivative of the position, that'll give us our velocity function. So if we differentiate this s function to come up with our velocity function, well, if we differentiate the 160t, that just turns into 160, minus on the back end, if we use the power rule, drop the 2 down as a multiplier, so that turns into 32, subtract 1 from the power, so that just becomes t. So the velocity function is 160 minus 32t. Now, if we're trying to figure out when the velocity is 0, then we would just set this equal to 0. So 0 equals 160 minus 32t. I'm going to add that 32t over to the left-hand side, so we get 32t equals 160, and then I'm going to divide both sides by 32, and when I do that, I get a t value of 5. So at a time of 5 seconds, our rock has a velocity of 0. Now, that doesn't actually tell us how high this rock went. This tells us the time that that maximum height happened. So now I need to take that 5 and plug it back into that height function. So to find the height, I'm going to take 160 times 5 minus 16 times 5 squared. And when I do all of that, I should get a maximum height of 400 feet. So at 5 seconds, the rock hit a height of 400 feet. Now, the next thing that we're going to look at doing is finding the velocity and the speed of the rock when it's 256 feet above the ground on the way up and also on the way down. The first thing that we're going to have to figure out is at what times is this rock 256 feet above the ground. So we're going to use that original position function where it's s equals 160t minus 16t squared. But what we're going to be doing is setting that equal to this 256. So I'm going to go 256 equals 160t minus 16t squared. Now I'm going to move my variables over to the left-hand side, mainly because I don't want to have a negative t squared. So I'm going to add that over and then subtract the 160t over. So we're going to get 16t squared minus 160t plus 256 equals 0. Now we can actually do some factoring in here. We can pull out a GCF of 16, and that's going to leave me with t squared minus 10t plus 16 equals 0. And actually we can do some sum and product factoring with that stuff inside of the parentheses. So we get 16 times, we're breaking this up into 2 separate sets of parentheses. This is going to be t minus 2 and t minus 8 equals 0. Now to solve for these times, we're going to set everything equal to 0. When I take the 16 and set that equal to 0, that doesn't make any sense, so we're just going to ignore it. Take the t minus 2, set that equal to 0, and we get a time of 2 seconds. Take the t minus 8 and set that equal to 0, and we get a time of 8 seconds. So the 2 times when we're at 256 feet above the ground are at 2 seconds and at 8 seconds. But now if we want to find the velocity of our rock at these 2 times, now we're going to have to use our velocity function. So that was 160 minus 32t. If I start with that t value of 2, then this would say my velocity is 160 minus 32 times 2. And if we simplify that down, we end up getting 96 feet per second. But then if we also use our time of 8, this would say v equals 160 minus 32 times 8, and we get negative 96 feet per second. So on the way up at 2 seconds, the velocity was 96 feet per second, but on the way down at 8 seconds, it was negative 96 feet per second. And that should make sense. Positive velocity means we're going up. Negative velocity means we're going down. But now we also asked about the speed. And what we have to remember is that speed is the absolute value of velocity. So at both of these times, at 2 seconds and at 8 seconds, the speed would be 96 feet per second. Next thing we're looking at is what is the acceleration of the rock at any time t during its flight after the blast. So remember, we had that position function s. That was the original thing that we were given, which was the 160t minus 16t squared. And then, in order to find our velocity function, we took s and we differentiated it. So we got 160 minus 32t. Well, if we want to find acceleration, acceleration is the derivative of velocity. or it's the second derivative of the position function. So if we differentiate this velocity function that we just came up with, we're going to get negative 32, and this would be labeled feet per second squared. Now, since the acceleration is negative, here's what that means. As soon as this rock gets blasted up, it's already starting to slow down because gravity is pulling down on it. But once it reaches its highest point and then starts falling, now it's actually increasing its velocity as it's going down because gravity is pulling it down faster and faster. And then the last thing we're looking at is when does the rock hit the ground? So this rock blasts up, hits its highest point, turns and comes back down and hits the ground at some point about right here. Now when the rock hits the ground, what's happening is that the height is at 0. So if we use that position function or that height function and set it equal to 0, then we should be able to figure out the time when the rock is hitting the ground. So if we do 0 equals 160t minus 16t squared, I'm going to factor the right-hand side, and I'm going to take out a 16t. So if I do that, I'm going to get 10 minus t. Setting both of these equal to 0, 16t equals 0. Dividing the 16 over, we get a time of 0 seconds. So that's right here before the blast happens. And then if I set the other one equal to 0, 10 minus t equals 0. Add the t over to the other side, we get a t value of 10. So at 10 seconds, the rock has come back down and hit the ground. That's going to be it for this video. Thanks for watching.